Nous avons un conférencier très spécial ce soir. Now, the bad weather is a bit unfortunate in that it will prevent us from viewing the comet this evening, but rest assured that there will be plenty of opportunity for questions and answers at the end. Also, the museum's observatory will be open for those who would like to just take a look at the telescope, the 15-inch refractor. Malheureusement, la tempête ne permet pas l'observation de la comète ce soir. La causerie sera légèrement allongée avec une session de questions et de réponses à la fin. L'observatoire sera ouvert aussi pour ceux et celles qui veulent voir notre lunette astronomique. At this time, I would like to welcome Mr. Terence Dickinson. He is a renowned astronomer, author, writer, current editor of the museum's Sky News magazine, and recipient of the Order of Canada. For a talk this evening on the comet Hale-Bopp. Mr. Dickinson.
Thank you very much, and good evening. You were scattered by a little bit of comet dust on your way here. You know that snow, and the water on this planet might be largely from comets. That's one thing I'm going to mention tonight. One new theory is that, relatively new, it was propounded about 15 years ago, is that comets that hit Earth during its early history brought most of the water to this planet. So that we, in effect, are comet life, because of course life began in the water. Maybe even was transported here by comets. That's going a little bit far, but it is not considered an outrageous idea, just one that has yet to be proven. Comets are an amazing phenomenon of the solar system. And now we get a chance to see one as bright, perhaps even brighter, than Halley's Comet was in 1910 when it was at its best. This is the first comet since 1910 to be visible prominently in the evening sky with the same brightness roughly, as Halley's Comet. Looking back through the records, there have been brighter comets, but they haven't been prominently positioned in the evening sky like Halley was, making that historic 1910 encounter that for generations, perhaps you were regaled by parents and grandparents who saw it, told you over and over again how wonderful it was, and then when it came around again in 1986, you went, "What, is that it?" Of course, when it returned, it was much farther away from us than it was on its 1910 visit, so we didn't get a good look, particularly here in the Northern Hemisphere. The case with Hale-Bopp is the Northern Hemisphere is the place to be. The latitude of Canada is ideal. For once, we're in the right spot at the right time. Now, before I continue any further with the comet thread of this talk, I always like to put news items in. And the two news items that I'd like to share with you right now are the close approach of Mars and the lunar eclipse that occurred last Sunday. And I have pictures of both. So if we can dim the lights right now, we'll go to those first slides. And this is a brand new, completely new Hubble telescope picture of Mars, and it is considered to be the finest picture of Mars ever taken. It shows incredible detail. I'll just point out a few features. This is the prettiest side of Mars. These, of course, are the famous deserts of Mars. These dark areas for most of the last century, and actually most of this century, were considered by many to be vegetation, because just in comparison to this desert, which looks like an Earth desert, this stuff looks the color, roughly, of vegetation. And here's one of the polar caps of Mars. And this is the polar hood. For the south polar region, this is a carbon dioxide haze over the polar region. All of these features are visible in small backyard telescopes. In fact, this side of Mars, with this main feature here, Syrtis Major, is the darkest and most prominent and obvious feature on Mars, and the first one ever seen by a telescope. It's the first feature ever drawn on the surface of the planet by the first telescopes used in the 17th century. This is what you'll see through a reasonable telescope, what you would have seen tonight if the weather had cooperated, and what you will see for the next week or two. The reason is that Mars's rotation is almost synchronous with the Earth. It's got a 24-hour, 24.7-hour rotation period compared to Earth's 24-hour period, so the same features are seen roughly in the same place from night to night, gradually cranking their way around. Syrtis Major and Sebaeus Sinus here, and here is just a wonderful detail on what's called the polar cap collar. And for Percival Lowell, the astronomer at the beginning of this century who was most involved with the theories of life on Mars, when he saw this through his telescope, his 24-inch refractor telescope at Lowell Observatory, which still exists, and if you're ever near Flagstaff, Arizona, you should go to this observatory. It's open virtually every day of the year. You can go in the observatory where Percival Lowell discovered and developed his theory of the canals of Mars. You can stand and look at this telescope. It's essentially the same way it was at the beginning of the century. And what he saw was, when he saw this, he thought, well, this must be ice. And as the ice melts, it feeds the vegetation. And his theory was that this is a dying planet, a planet where there's mostly desert and not enough water. Well, in some ways he was right, because, and I'm not going to get into a talk on Mars tonight, but there's so much interesting about this planet, and it's so close to us. But the one way that he was right for the wrong reasons was that we now believe that Mars was much more Earth-like in the past. It had liquid water on its surface. We can tell this by close-up photos showing ancient riverbeds, and now has become drier and cooler. And perhaps all of the water is still there, but as permafrost underneath the ground, and a little bit of it is the polar cap, which is some ice and some dry ice, frozen carbon dioxide. These dark areas are deserts as well, only they're rougher deserts, rocky deserts, and made of darker material than these light sandy and dust deserts. Anyway, I wanted to show you this. This is sort of hot off the press. It was taken on March the 12th by the Hubble Space Telescope and just released 2 days ago. And in the next slide, we have the lunar eclipse from Sunday. You can just see the full moon just at the edge of the Earth's shadow. There's the edge of it right there. Do you notice a little bit of darkening on this side of the moon? Slightly? Just a little bit? On the next slide, you can see now the moon is moving in this direction into the Earth's shadow. Now, I know many of you saw this. I'm going to ask for a show of hands after the lights go back up as to how many of you did. In the next slide, we see now what was happening here. The moon is passing through the Earth's shadow. Only in the eclipse on Sunday, it didn't quite get all the way in. Just a little bit at the northern part of the moon remained outside the shadow. But the shading of the moon that you saw, if you saw the real eclipse, which peaked at 11:40, you would have seen a beautiful shading, a copper color shading to the eclipse. Now this is a shot that shows what was left. Here's the Earth's shadow. Hardly any of the moon is left in shadow. This exposure just shows what was remaining, about 8% of the moon. The next exposure, which in comparison, that one was about a 60th or a 30th of a second. This is a 35-second exposure. This is way overexposed the section that was not in the Earth's shadow, but here's the Earth's shadow perfectly exposed and showing its color. And when you looked at the moon, particularly in binoculars, it was this marvelous, rich, coppery hue. And what that is the red component of sunlight filtering through and getting through the Earth's atmosphere and being refracted into the Earth's shadow, just as we see in this view here. You can see how the sunlight that gets through is bent or lensed or refracted into the shadow. But it's only a very small percentage of the total amount of light that reaches the moon under normal circumstances. Okay? We'll have the lights back up now, please. And we can turn that slide off for the moment. So, those were some recent events brought to you at great expense and effort. I always like to be able to show the newest stuff. And now it's your turn. How many saw the eclipse? Looks like about 80% of the audience. How many of you stuck around for mid-eclipse at 11:40? Not so many. I know that's a little late for some people's schedules, but that's the time when the color was at its best. How many of you have noticed the planet Mars in the night sky, identified by its color, its orangish color? Terrific. Now, those of you who haven't, you can see it high in the east, anytime from about now on, 7:30 on. A little low in the east now, higher in the southeast later in the evening. Very bright. It's at its closest now for the next 2 years. Every 2 years, Earth catches up to Mars and it appears bright in the sky. How many of you have seen Comet Hale-Bopp? That looks like a 100%. I want to assure you that you haven't seen the whole thing. The whole show is far from over. The best is yet to come. Unlike what you probably heard in the news media, over this past weekend, I heard many stories saying the best time to look at the comet was this past weekend when it was closest to the Earth. The best time to look at the comet was during the partial eclipse of the moon, which of course was only true for the west coast of Canada and not true for the rest of the country because the comet was below the horizon. Yeah. So you needed X-ray vision in order to see a comet at the same time the eclipse was occurring. Anyway, ignore that business. Many things were wrong. Yes, the comet was closest to the Earth, but comets are brightest, generally speaking, when they're closest to the sun, which is coming up at the end of this week. And this distance won't be that much different from what it was at the beginning of the week. The moon was full early in the week, this past weekend. Full moon means the sky's completely lit. The comet's difficult to see. Yes, it would have been nice if during the partial eclipse the comet had been visible, but it wasn't. So, a lot was wrong with those reports, and somehow they got started, and it was like a snowball rolling down a hill, and I think everybody, right? How many of you heard those reports? Yeah, about half or more. Okay. Now like I say, we spare no expense here. This is one of our props. This golf ball. Here's another one I absconded with the custodian's broom handle. And just to complete my extraordinary props list here, I have a ballpoint pen. This will represent the sun. And we can build a scale model of the sun, the inner part of the solar system, and Comet Hale-Bopp and Comet Hyakutake of last year. How many of you saw Comet Hyakutake last year? We've got a terrific audience. These huge majorities, that's what we like to see. Bit of a selection effect here, no doubt, but I'm glad to see those large numbers. Okay, if the sun is this big, the Earth is the size of the ball in this ballpoint pen. That's as close as you can come to a correct scale model. The Earth's pretty puny compared to the sun. But of course, the sun is the ruler of the solar system. It's the most massive object by far in the solar system. And at this distance here is the planet Mercury, a little bit smaller than a ball in a ballpoint pen. It takes 3 months to make one orbit. And at this distance is Venus. And at this distance here is the Earth, roughly about this far away. Good. We've got illumination on the Earth now, and the props do work. And so 1 year to make one orbit of the Earth. There's correct scale distance. Now, on this scale model, Comet Hale-Bopp's tail is this big. 50 million kilometers long. And as wide or wider than this stick. We're dealing with a colossal, immense object. Now, I'll tell you where it is, and if I could have a youngster come up and just hold this pen in position. Sure, come on. What's your first name? Drew. Okay, Drew, if you just stand here and stand around here where I was. That's right, and hold that out there. Perfect. Now, I'll position this correctly for where the comet is right now. Danger pay is provided by the museum. Something, I'm close, something like that. And note the angle, tilted back away from us. Roughly, I think I'm close. It's farther from the sun than I'm showing the head of the comet, but I can't reach. It's actually well up into the ceiling there, in this position. If I just extend this another broom handle back, that's where it would be. And above the plane of the solar system, all the planets orbit in the plane where Drew is holding the Earth, like this. The solar system and the planetary system is in a flat plane. Comets are total renegades. They don't care about the plane of the solar system. They come flying in from any direction. And Comet Hale-Bopp is going to come, it's coming down right now, and is going to go through the plane of the solar system, near the Earth's orbit, but over on the other side. If, just imagine this, if the Earth was at the point in its orbit where Hale-Bopp comes when it intersects the plane of the solar system, it would be, and it's only about as far as Drew's head from the Earth, where the intersection point occurs. It would be like that. It would have been almost scary. It would have been something like magnitude -6 to -8, which is brighter than anything in the sky except the moon. And this tail would have been awesome in the sky, visible during the daytime. That's a little too close. And there has never been a comet as big as Hale-Bopp that gets that close. I'll just have you stand there for just another moment, Drew, because I want to show you where Comet Hyakutake was. And now, I need something a little bit smaller, a little bit longer than a pen, but I don't have anything between the pen and the broom handle. Comet Hyakutake came on a fantastic orbit that carried it like this. Here's the tail and the head of the comet like this. And it came like that, right over the Earth. But it was a little comet. Comet Hyakutake was almost as bright as Comet Hale-Bopp, but it's almost a miniature comet compared to Hale-Bopp. But Hale-Bopp is 13 times farther away at its closest approach, as it was last weekend. So that's why the two of them are generally in the same scale of brightness. One was small and close, the other one's gigantic and far away. Hale-Bopp is considered to be the biggest comet seen since either 1377, the 18th century, or a previous comet in 1577. One of those two were about the same size. Okay, thanks very much, Drew. And so this gives you sort of a scaling of the relationships to these objects. Now, of course, the question is, how the heck can something like this big come flying into the solar system? I mean, you'd expect there'd be havoc. Its gravity would be tearing all the planets out of their orbits. This whole thing, the whole tail of the comet, is vapors. It's gaseous vapors from the icy nucleus and dust that was embedded in the ice. And I'll be explaining all of this structural business in a minute. But the solid object at the head of the comet, the nucleus, is about 40 kilometers in diameter. That's a big chunk of ice relative to humans, but on a cosmic scale, it's relatively small. And when it gets close to the sun, this close, it would be almost completely vaporized, the whole thing. But it doesn't get that close. It gets 2 broom handles away, which is roughly the same distance as the Earth is from the sun. And at that distance, just the top couple of meters, or tens of meters, of the comet is vaporized. The tail of this substantial length and size, you can see its width when you look at it. You've all seen that. So it looks big. You could make that object if you took about 1,000 dump truck loads of snow from Ottawa streets, transported it out into space by rocket, and then set it there and let the sun melt it and the solar radiation blow it back into the tail. 1,000 dump truck loads make something 50 million kilometers long because it's in a vacuum. It's not blowing against anything. It's not pushing against anything. There's nothing to stop the vapors from expanding into an a sun-sized head, and then blowing back into a tail that's as long as the distance almost between 2 planets. So these are amazing objects, and one astronomer who, after this was finally figured out what the heck comets are, he announced that comets are the closest thing to being nothing while still being something. And that's probably a pretty good description of them, because in the case of Comet Hyakutake, you probably only had a couple of dump truck loads of vapors involved. Because there's a little comet, this is a big one. So there, in a nutshell, is where and what these things are. But I got a nice slideshow, and in addition to that, a fabulous video made by 2 amateur astronomers locally from Ottawa, actually with the help of quite a number of people locally here in Ottawa. Fantastic video, the best comet movie that has ever been made. And it was made right here. So I'm delighted to be able to, for most of you, premiere this video and describe it to you. So we got a visually packed show. So let's dim the lights and go back to the slides. And imagine ourselves, unlike tonight, watching the sunset, crescent moon become visible, and anticipating the appearance of Comet Hale-Bopp. Let me just run through a couple of scenes. Let me ask you at this point whether this light over here that's illuminating the podium is dimming the slides, or can you see them okay?
Okay.
Would you like the light out, or is it okay? Most people say it's okay. All right, so we'll continue. And if you feel that you're not getting the full benefit of the slides, it is okay if we turn out that light. We're making a video of this presentation, but it can be done in the dark too. So, as we go along, if anybody wants to change the lighting in here, just speak up, because I want you to get the full benefit of these fabulous pictures, since I took most of them. Well, this is the conjunction of Venus, Jupiter, and Mars, a spectacular triple planetary grouping of three fabulously bright objects back in June of 1991. And the next night, the crescent moon nestled right in here, but of course it was cloudy that night, where the very best shot could have been taken. Now we fast forward up to about 8 nights ago. In the morning, just at the crack of dawn, there is Comet Hale-Bopp, displaying spectacularly its two tails, its gas tail and its dust tail. And as I mentioned earlier, the comet nucleus buried here in the convergence of the two tails is made of ice, something about 40 kilometers in diameter. But here, from here to here, is 30, 40 million kilometers, because this thing's a long way away. It's 200 million kilometers away. The sun is 150 million kilometers away. That's something like more than 500 times farther away than the moon. And what we're seeing is sunlight illuminating this dust and gas, and it's particularly, the dust is a wonderful reflector of sunlight, just like dust that shines in the shaft of sunlight. You can hardly see the speck of dust, but when sunlight reflects off it, you can see it from the other side of the room. Let's move outdoors farther, not only outdoors, but farther away from any city illumination, and leave the city glow behind. And we're going to transport ourselves even deeper by going to a mountaintop in Arizona. Let's go to the next slide, please. Where we observe the swath of the Milky Way across the night sky. Now, this was taken from a 7,000-foot mountain in Arizona, coincidentally, where the same place that this Comet movie that I'll show you a little later was taken. And the clarity of the sky, enabling pictures like this to be taken, is amazing. And the altitude is something that we don't get in the eastern part of North America, which allows you to view an exceedingly clear atmosphere. What we're seeing here is our own galaxy edge on. The central hub of our galaxy and the convergence of the spiral arms of the galaxy are all mixed in to form this beautiful pastoral scene. And I'm hesitating here because I have a balky advancer for my slides, so we'll proceed. Here is about where we are in our galaxy. If we imagine ourselves looking out the window of an airplane, flying above the clouds, about 100,000 light years from our Milky Way galaxy, and looking back on it, that's what we would see. And there we are. our sun in about the third winding out. And when we had that previous view, we were looking at this section in here, the brightest part of the galaxy, and looking at it edge on. Here's another galaxy, not ours. Of course, we can't photograph our own galaxy, we're in it. Like trying to photograph Ottawa from standing on Bank Street. You're only going to see the buildings, which is the other stars. So we would be roughly here if we were in that galaxy. Next, please. There's another view, exceedingly wide-angle view, showing the galaxy almost wrapping around us. There's the hub, and there's the edge-on view. The winter Milky Way, much paler. This was taken from my backyard rather than in a mountain in Arizona. But it still shows up, but much paler because we're looking mostly outwards in the galaxy. You'll recognize a familiar group of stars here. Orion, the three-star belt of Orion, the two shoulders, two knees of the giant, and his sword here. And we'll take a closer look at that in the next slide. Here's the three-star belt. There's the sword, the Orion Nebula. I know many of you who are stargazers, of course, have noticed this before. It's visible to the unaided eye, and it is also visible in binoculars as a little cup-shaped cloud of gas and dust. You don't see the color. The eye isn't sensitive to that unless you're using a very large telescope. Another view of it, telescopic view. So the whole purpose of this little tour is to sort of give you your place in the scheme of things, and now we're going to zoom in into the core of the Orion Nebula, which is a star-forming region in our part of the galaxy. We're getting closer in. This is the trapezium telescopic view of 4 stars in the heart of the nebula, and this cloud of dust and gas is being illuminated by those stars. And now we're right inside, deep inside, a Hubble telescope shot that not only shows the interior of the cloud, but these 5 objects here, which are believed to be stars in formation, and solar systems too, planets along with those stars. These are cocoons where the cloud is collapsing and stars and planets are forming from the material in those clouds. And this is how our solar system was formed. This is how we think all stars that we see in the sky have been formed since the creation of the universe roughly 10 to 15 billion years ago. Here's an artist's concept of what goes on inside the cloud. Here's the sun in formation, disc-shaped cloud of material swirling around. Some chunks have formed out of collection of the material in the cloud, which is dust and gas. The dust sort of being like windowsill dust, only it's the windowsill of the universe. It's the stuff that is solid particles that collects in these clouds. And eventually, our Earth and Moon formed out of this material. And early on in the history of the solar system, we're talking about the first 500 million years, there was lots of other stuff left over from the formation of the planets. And that stuff pounded into the planets, hammering them. And what we see today, the tranquility that we see today, is far different from what it was early on. Well, during this, here we have a view from today. Crescent moon, Venus, Mars, Jupiter. This was before they came into that triangle that I told you about earlier. This is about a month earlier. But what this shows is how the planets are aligned to what we call the ecliptic, the plane of the solar system. I mentioned earlier that the solar system is the planets orbiting the sun is in a flat plane. And that was that disc-shaped cloud that you saw. The planets orbiting the sun have maintained the momentum of that cloud and its structural integrity, because once they formed and the material of the cloud got blown back by the sun in its early days, there was nothing to stop them, nothing to divert them from this. So today we see the planets as if they're all balls rolling around on a billiard table on a flat surface, only it's angled because of where we are on the planet. If we were at the North Pole, they'd be running along the horizon, and if we were at the equator, they'd be standing straight up. So since we're halfway, we see them roughly at a 45-degree angle, although it changes during the year. Next one, please. Thanks. Now we move outwards from the inner part of the solar system, where we are, in here. Jupiter, Saturn, Uranus, and Neptune's orbit, and the orbit of Pluto. And now, finally, getting out to the comets. I wanted sort of to give you the origin and the place of all this, to have some relative sense of context of how all this fits into the scheme of things. All these little specks here in what's known as the Kuiper belt are believed to be comets. Some of the very largest of them have been observed. There's about 60 of them that have been observed beyond the orbit of Pluto. Well, not exactly beyond it, as you can see here. Beyond the orbit of Neptune, but not necessarily beyond the orbit of Pluto. In fact, Pluto ranges right out into this realm of the comets. And in doing so, if it were discovered today, Pluto would be regarded as a comet, almost certainly, the largest member of the Kuiper belt. But since it was discovered in 1930, and these other things weren't discovered until the 1990s, there's been 60 years of having Pluto in the textbooks as a planet. And that's the way it's going to stay. Astronomers have decided that they're not going to trash all of the mentions of Pluto as a planet, because it now appears to be rather more clearly classified as the largest member of this massive arrangement of planets, of comets, rather. So the realm of the comets begins where the planets end. In the Kuiper belt, there could be millions, almost certainly are millions, could be billions of them. Typically a couple of kilometers in diameter. And essentially what these guys are the leftover material from the formation of the planets. The gravitational interaction of the planets in the inner solar system has knocked out all of these objects that happen to be formed in here. In the outer solar system, the gas giant planets have large components of water and ice in them. And so there was plenty of opportunity for other comets to be made in here. But today we find almost none in there. There's one called Chiron, and a few others. I think there's only 5 of them known that orbit in between these giant planets. The rest of them are out well beyond the Kuiper belt in another zone called the Oort cloud, named after Mr. Oort, who first suggested that it was there in 1950. So there's 2 realms for the comet, the comet families. The first one, the Kuiper belt, these comets are where they formed. They're basically where they were born. The next zone beyond them, the Oort cloud, are comets that were probably thrown out of this region by gravitational interaction of the giant planets and flown out into vast orbits that only return back to this region on very rare occasions because they have orbits of millions of years. Sometimes, though, when they do come in, and they get perturbed by the gravitation of one of these planets, they can come in closer and closer and reach the inner part of the solar system where Hale-Bopp is now. Get into this orbital evolution a little bit later. Here's an artist's concept of what a comet looks like in the Kuiper belt or the Oort clouds, the sun very bright in the view, and this little chunk of ice. It's not like an iceberg, it's more like a snowball. Actually, the edge, the gutter of a typical street in Ottawa would be pretty good comet stuff, because it's ice, but in the form of snow, with dirt mixed in, with dust. Here's another artist's concept, showing a comet when it gets close enough to the sun, where sunlight begins to vaporize the icy material. And here's an actual photograph of Halley's Comet made by a spacecraft. It's shaped like a peanut. The comet, about 18 kilometers long, the nucleus of Halley. And remember, Hale-Bopp's about 40 kilometers, so it's about this big in comparison. So it's much, much bigger. And here's the side with the sun shining on it. You can see that there's preferential vaporization here, where the vapor jets out. And what's believed to be going on here is that the surface gets heated and it melts or vaporizes the ices underneath, and then they shoot out through jets, as illustrated here, where you have the surface being heated by the sun, but underneath is where the vapors actually get heated more because of the transmission of the heat through this dark and dust-covered surface of the comet, and then boom, these jets go swishing out and produce the comet phenomenon. Now here's an actual photograph of that going on, where you can see the jets. This was taken with a 6-inch telescope in my backyard observatory. This is Comet Hale-Bopp last November. And it had very prominent jets emerging from it. And that is believed to be the manifestation on a large scale of the phenomena that I just showed in the last slide. Well, a quick review of some other comets of recent history. This was the comet of the century of 1974. And you can see that it clearly didn't live up to its reputation or predictions, because this was it at its brightest. This is Comet Kohoutek, which was supposed to be at its brightest on January the 4th, 3rd and 4th, 1974. And although you could see it in binoculars, you can see here that it was pretty puny. The predictions of its brightness were only off by a factor of 10,000. And it made astronomers look pretty bad. Because the predictions were made in advance, like they were for Hale-Bopp, same sort of thing, discovered well in advance of when it was going to be closest to the Earth. And during that time, Hale-Bopp has essentially lived up to its predictions. This comet fizzled terribly. But we only figured out what comets were, the structure of comets and their makeup. The modern model of comets was only developed in the early 1950s. And Comet Kohoutek was only 20 years after that model had been developed. So we were still pretty young into the idea of what comets are. And the same fellow, Brian Marsden, an astronomer at Harvard, who made the prediction for Kohoutek and was off by a factor of 10,000, made the prediction for Hale-Bopp and was off by a factor of 2. So he's clearly learned something in a quarter of a century. And good for him. Well, here's another fizzle. There it is. There's the Andromeda Galaxy. And this little puny wimp of a comet was Comet Austin of 1986 or 87, I've forgotten. This time astronomers kept quiet about this one. The predictions were made. In fact, I remember the headlines in Sky and Telescope on the cover. It said, "Monster Comet Coming." And this was it. This is your monster comet. But fortunately, those kinds of headlines didn't get much farther than the astronomy magazines, and the predictions were corrected. Here's another puny comet. This is my backyard, showing just in a slightly different direction from the last slide, showing Comet Halley, Halley's comet, in the morning sky. Again, very poor performance, but this one was predicted accurately. It's just everybody thought, if it's Halley's comet, it's got to be good, because we've heard so much about this, but astronomers knew it wouldn't be, because it was well on the other side of its orbit. The Earth and the comet were on opposite sides, and so not having a very good relationship in terms of staying standoffish. Next slide, please. Comet Levy of 1990. This was a nice comet. It was high up in the sky. It didn't produce much of a tail, but it was visible to the unaided eye, and also followed the predictions fairly well. Modest comet, discovered by the famous Canadian comet hunter David Levy, whose name was attached to one of the most famous comets of all time, Comet Shoemaker-Levy, that crashed into Jupiter. This was a truly great comet. I didn't take this picture. This was taken from Arizona. This is the spectacular comet Ikea-Siki of 1965. In Canada, when viewed from Canada, the horizon was up here. It's because of our different position on the globe. And so the comet was not seen anywhere near this well, but this was a comet with a spectacular long tail. And was a pretty interesting object to view, but we didn't get a very good look at it here. Next, please. Conversely, this was Comet West of 1976. And this picture was taken by Kathy Hall, a resident of Ottawa, only it was taken from atop the dormitory building at the University of Victoria. Fortunately, she was there, and unfortunately, we were here, because if we were taking the same picture, we would get the kind of... Oh, that was my golf ball. That just fell off. Yeah, the sunset. Good, clever. You can see a Comet West's tail extending way up into the twilight. This was the last comet that was as bright as Hale-Bopp. This comet at its maximum was easily visible in twilight, just like Hale-Bopp is. But it was only visible for a couple of days, and at 5 a.m. in the morning, and only, I think, 15 months after Comet Kohoutek. And the media wouldn't touch it. There was nothing in the newspapers or on TV about this comet, because they had believed the astronomers the last time with Kohoutek. Well, this comet turned out to be brighter than the predictions. But nobody saw it except people who were astronomy buffs. And even then, it was only visible for a few mornings at its best in early April of 1976. And then, on top of that, we had terrible weather here in Ontario, and a lot of people didn't see it. Although Rolf Meyer, local astronomer of note, got a great picture of it as well from Ottawa, but not many people did from here. So that's the last big one. Oh, this is a photo by Sky and Telescope magazine's Dennis DeCicco showing Comet West, a magnificent comet. And Hale-Bopp is in exactly the same category. and it's going to be visible longer. So the consensus is, unfortunately I didn't see this comet at its best, so I can't vouch for this, but the consensus is that Hale-Bopp exceeds this. It also was a morning sky comet, and so we do have to go back to Halley to really get a comparable situation to what we have now. Okay, now we come to Comet Yakutaki, which was visible last, a year ago exactly, to this very week, sporting a wonderful tail, but mostly being bright because it was so close to us. That's not to denigrate it in any way. It was a stupendous comet. Well, here's what happens then, just in a stylized way. Comet comes in its orbit. The orbits are very eccentric or elongated, so that a small portion of them comes in the inner solar system, and most of the orbit is far out. It's just the nature of comets. And as they come in, you can see that the tail points away from the sun, which is the source of energy that's knocking the tail back. It's got nothing to do with which way the comet's going. Comets look like they're whooshing through something, but they're not whooshing through something. Something is whooshing them, and that's the sun. And it's sunlight and the solar wind that's pushing this tail back. So they come in head first, and they go out tail first. Here's the orbit of Halley's comet, just to give you an idea of what a comet orbit looks like, the complete thing. Very elongated and sausage-shaped. Here's where Halley is right now. It's out around Neptune, and was in here in 1985 and 86. But you can see, here's the orbit of Mars, and the orbit of Earth is just inside. Earth was here when the comet was over here. Now that's the way it is with Hale-Bopp as well, except that Hale-Bopp's significantly bigger than Halley, and we still get a good view of it. Hale-Bopp's orbit also, on this scale, would extend, let's see, about past the intersection out here at Saint Laurent Boulevard. Its orbit was 4,000 years since the previous past. That is, here it is today. The orbit goes way out, and 4,000 years ago it was back in here. Well, the way it's going to work this time is after the 4,000 years, Hale-Bopp comes in and then goes out, but its orbit has been modified by Jupiter, and I'll explain that a little bit later about how that happens. And the orbit is now about 2,380 years, as opposed to 4,000 years. So somewhere back when they were thinking about the pyramids, that's when they last saw Hale-Bopp, and who knows what will be going on in the year 4,380. Next, please. Well, now we'll get specifically to Hale-Bopp's orbit. This is a scaling that shows very different scales here. Nucleus of the comet, the whole comet structure, compared to this little tiny circle is the moon's orbit, compared to the size of Hale-Bopp. So that is the room handle. There's Hale-Bopp now compared to the inner solar system out to Jupiter, and its section of its orbit compared to the outer solar system, and now the complete orbit compared to the Kuiper belt, and you can't even see the complete orbit compared to the Oort cloud. So let's go to the next slide, please. This shows the bottom section. Now, here's the Oort cloud. This thing is at least a light year across, which is 40 trillion kilometers. Easily that wide. Contains something like 1 trillion comets. Their combined mass would be perhaps 10 times the mass of the Earth. Now the Kuiper belt, its combined mass could be about the mass of the Earth. And here's Hale-Bopp's orbit. This point out here is about 500 times the Earth's distance from the Sun, and roughly a 4,000-year period, which has been now modified to a little over 2,000 years. Now, the inner part of the Kuiper Belt and the planets out to Neptune, Pluto's not shown, and you can see how the orbit of the comet does not pay any attention to the plane of the solar system, and neither does the Oort cloud. So that's where these guys come from, that don't pay any attention to it, because they're all scattered out here, because they came from in here and got bumped out by the gravity of the giant planets. They made a close encounter with a giant planet, and then whoop, they're gone, and they're stuck out here in the Siberia of the solar system. So here's the inner part of the orbit. Now we got a better view. I think in the next slide we see a better view again. Yes, here we go. All right, so there's the Kuiper Belt section of the orbit. Now we go close up to the inner part of the solar system, and here's Hale-Bopp's orbit. Actually, since this diagram was made about 8 months ago, the orbit, as it dives through the plane of the solar system, comes just outside the Earth's orbit rather than just inside, as shown here, which would be even more interesting if the Earth was right there, because it would be in the night sky spectacularly. Here's where it is now. And there's a little dot here, right there, showing where the Earth is. So you can see we've got to look above the Sun. That's about 200 million kilometers there, and about 150 million to the Sun. The Earth's direction of motion is this way. So the Earth moves away from the comet as the comet comes down here. So we could be positioned a little bit better, but it doesn't really matter. This comet is so big, it doesn't really matter where the Earth was in its orbit. We'd get a reasonably good view of it. Next slide, please, Adrian. All right. Now we have a close-up view of the comet showing its gas and dust tails, at least in illustration form, and then the solid nucleus, which is a tiny little speck in the center here that we can't see because of all the vapors around it. The solid part has not been imaged, so far as I know, or imaged by radar either, which they sometimes do. Next, please. This is a postcard from Gary, Indiana, back in 1910, showing Halley's Comet. And even then, they had to contend with a little bit of light pollution, although it doesn't appear to have affected things too much. The lights were pretty dim then, and the comet was visible above Main Street, or at least Fifth Avenue and Broadway, that says here, on May 20th, 1910. And this is what we're seeing this time. This is the same sort of phenomenon. Hale-Bopp is certainly the first comet in my memory, and I think it's correct to say the first evening sky comet since Halley's Comet that's visible to anybody, no matter where you are in the northern hemisphere, city or country, you can still see it. Okay, a little review then, and bring us up to speed on Hale-Bopp. This was last year with Comet Hyakutake. My first view of it as I stepped out of the car onto this country road after driving out from under the clouds over here. I live north of Kingston. I drove toward Toronto when I found out by phoning somebody in Toronto that it was clear there. It was cloudy in Kingston and clear in Toronto. It's got to be clear somewhere between the two cities, so I started driving after a week of cloudy weather. Please, I hope we don't have to go through this again. But I just heard the long-range forecast, and it's clouds as far as they went, like up through next Sunday. And I'm saying, no, the comet's going to be at its best starting on tomorrow, Wednesday. So I may get desperate again and have to drive somewhere, or fly. I phoned the day before this. I phoned somebody in Thunder Bay, and was prepared to fly to Thunder Bay because I found somebody who said, yeah, it's clear. It's going to be clear tonight. It's clear all over northwestern Ontario. But of course, if you fly at the last minute, you get slapped with the business fares. And to fly from Kingston to Thunder Bay is just a few dollars under $1,000 when you take the last minute fare. That wasn't going to stop me, but because it looked like that was coming our way. So anyway, that was a long story to have to do with this little gravel road here, but here is from Sky News magazine showing the orbit of Comet Hyakutake, which has similar characteristics to Hale-Bopp. You can see there's the inner planets, and there's a section of the orbit, except for the fact that the Earth is here when the comet was here. And that's why it was so wondrous. It's just a regular run-of-the-mill comet. We got a nice close view of it. And that was the miraculous and wonderful thing. And if we go to the next slide, here is what it looked like. Now, normally, for a normal run-of-the-mill comet, you wouldn't see the tail. This is the gas tail of the comet, and it's pretty faint. But if you're close to it, it's visible. And here it is with its tail extending through the Big Dipper, as long as the Big Dipper. Magnificent. And it was visible, something that, unlike Hale-Bopp, next slide please, was visible all night. Here is a close-up view of the brightest part of the comet. Showing the nucleus is in here, you can't see it. So only 2 kilometers in diameter in any event. But it is being vaporized. The sun's over here, so the sun's shining this way, vaporizing the surface of this. It rushes outward because nothing's stopping it, and then gets pushed back. You can see this bow shock, as they call it, because it gets pushed back by the pressure, just the simple pressure of sunlight, and the solar wind, which is a wind of electrically charged particles, just bits of atoms that are carried out off the sun. And this is the gas tail, that little spike coming back there. The solar wind really attacks the gas because it carries a magnetic field with it and whips the gas back in a more leisurely fashion. The dust gets blown back. Next, please. This is a wonderful drawing from 1861. This was back at the time before photography, when astronomers spent a great deal of time drawing the features of a comet. And here is where the nucleus would be. Again, too small to see. Nobody's ever seen from Earth a nucleus of a comet. It's too little at those distances. And there it is, doing the same sort of thing that I photographed in the previous slide of Hyakutake. The sunward side bursts out these vapors, and then it gets pushed back into a tail by the pressure of sunlight, and the gas gets sent straight back. Not too much gas in the case of this particular comet. Now we're beginning to see the twofold phenomena: the dust and the gas. We see it much more clearly in the case of Hale-Bopp because the two tails are separated. The gas tail, though, on Comet Hyakutake was incredibly long. This is a very wide-angle photograph. Here is the Big Dipper, 25 degrees from one end to the other. This tail, to the unaided eye, was 65 degrees long. And it's at least 65 degrees. It's about 68 degrees long in this picture. Let's go to the next slide, because I enhanced the picture in order to show where the tail ends. And it's up here, that's 68 degrees from there to there. Just incredible. 68 degrees, that's like that on the sky. And we haven't seen anything like that since Halley's Comet either. So this was a remarkable comet that Hale-Bopp will not do this sort of thing. And that's because this comet was close to us. The tail wasn't that big, but because it was close, it looked big. And here it is not too far from Polaris. This was a wonderful night because it was visible all night. The tail pointed out this way early in the night. This was taken at 10 to 4 in the morning. And the tail had wheeled all the way around, pointed straight up around midnight. And then this was one of the most wonderful nights I think I've spent under the stars, watching this like the hour hand of a clock going backwards as it turned around in the sky. And by this time, I didn't notice that my feet were almost falling off from freezing, but it was this time of year and we had snow on the ground again. And I was waiting for the space shuttle Atlantis, and there it is, moving across underneath the comet. Now this picture was in Canadian Geographic and a number of other publications. Not only was this the Atlantis space shuttle, but the space station Mir was docked to it at the same time, and there were 2 astronauts out on a spacewalk. And when they saw this picture published in Space News magazine in the States, they phoned me to get copies of this picture because they said, this picture shows it better than we saw it. Apparently they tried to take pictures of the comet from the shuttle, but it was not an astronomical mission. The shuttle never stayed still enough for them to take the pictures. And so I sent them all souvenir pictures of them. That's them. And another beautiful Comet Hyakutake shot. This was on the 17th of April as it was heading down toward the horizon and was just sprouting, getting close to the sun too, much closer than Hale-Bopp gets, sprouting a fabulous tail. It was just a wondrous sight. And so far, for me, Comet Hale-Bopp has not matched the pure ethereal beauty of Comet Hyakutake and may not surpass it. It's just a different kind of comet and will produce its own kind of show and own kind of magnificence to us. These are 2 very, very different comets. Let's have the next one, please. Another Comet Hyakutake shot taken about April the 10th. Showing again the gas tail here, the blue gas tail, and the white or yellowish dust tail. Now they're superimposed on top of each other just from the angle that we were viewing this comet. Next, please. But now we go to Hale-Bopp, and we've got first of all, a different size and different distance and a different comet. That's what's so great about these objects. They're unpredictable, they're different, they're not fully understood yet. The last bastion of real mystery in the solar system, where no close-up information other than that picture of the nucleus of Halley's Comet has yet been obtained. No spacecraft has ever landed on one or taken really good pictures of the nucleus. So this is Hale-Bopp last November, showing its jet sprouts. Next, please. And this is a close-up of that illustration, purely suggestive of what the nucleus might look like if we could view it close up. Next, please. And here's a photograph showing, this is from February, showing again the phenomena of the bow shock. Now, lots of interesting things in the last month have been happening in here, close to the nucleus. And I've attempted to photograph it, and it's the job for a CCD camera as opposed to a film camera, which I use, and or drawing. And in the next slide, we see a drawing. This was made by Sherman Williams of Nova Scotia, and is a very low resolution image that I was quickly able to get of his over the internet. But it shows an amazing structure like a spiral galaxy in here. Here is the nucleus buried in here, and then some spiral bands, 3 of them, hoods, or shells are coming off it. These are being emitted. They're mostly, they've got to be dust emissions from jets that are coming out of the nucleus that is rotating like this counterclockwise. And we're looking down, roughly down on the pole of it. And as those jets are brought into view and they get heated and they shoot out material, it goes out in rings and then gets blown back into the dust tail. And this is a phenomenon that is visible in a 60 millimeter refractor telescope, very small telescope, a telescope that I generally relegate to the junk scope category, but any telescope will show this feature because this is such a gigantic comet. And exactly what's going on in here, I haven't heard a complete and thorough explanation yet because I still think people are scratching their heads over exactly the details of what's going on, but it's roughly what I just explained. Okay, now some photographs of Hale-Bopp. This is from February in the early morning sky. And again from February, but later, just a couple of days later actually, so we moved there from this star, showing a bit of the gas tail. And this is more recent. This is from a week ago Sunday, showing the gas tail and the dust tail separated. Now they were separated from Hyakutake too, but we were viewing one superimposed on top of the other. And here we get a nice separation of the two. The gas tail always tells you where the sun is. Let me get to the next slide, please. And we see a little more clearly here. The gas tail, if you just follow it back this way, that's where the sun is. The dust tail tends to lag a little bit behind because it gets blown back a lot more slowly than the gas tail does. It tends to be just a couple of days for the material to zip back here, whereas with the dust tail, it tends to lag and take longer. And so it has a gentle curve to it, which has something to do with the comet's motion, simply because the stuff is released and then the comet moves from the release point. This is a shot with a 300 millimeter lens taken again about, this would have been about 2 weeks ago. And you can begin to see some structure in the dust tail, or the gas tail rather, and a bit of structure in the dust tail too. I think we may get nice linear features. I'm already beginning to see them, striations that we saw with, and I think you can see some of them here, can't you? That we got with Comet West. So the comet will be at its best for the next 2 weeks or so, and it should look better than this, at least in photographs. And now this is a shot with about a 700 millimeter focal length on a 155 millimeter refractor telescope, again showing the gas tail and the dust section of the comet. Not too many features in here at all. It's pretty hazy, but you can see certainly some striations in here. Tends to be a lot more structure in the gas tail because it's being affected by magnetic fields and electrical fields from the solar wind. And this was taken just a few days ago in the evening sky as the comet was near the horizon, but the gibbous moon was in the sky, and of course moonlight is sunlight. It's just sunlight reflected off the moon, so it does the same thing to the sky as the sun does, only to obviously a far lesser extent, but it gives the blue cast of the sky anyway. Now the moon is gone, starting tomorrow night, and the comet will be there in all its glory above the clouds. I hate to have to say that, but I just know what's going to happen. Same thing that happened with Hyakutake, a whole week, and then everybody will be ready to do anything to see this comet. Okay, here's what happened in the orbit. This is how Jupiter, which is the main nemesis for comets, affects the orbit. The comet came in like this. Jupiter was here. Hale-Bopp went this way, ahead of it, and its orbit was modified by Jupiter's gravity so that it became smaller. Went from 4,000 years to 2,380, plus or minus a century or two. Not too accurate yet, but the comet was discovered out about here, and we followed it into here, and when we follow it out to here and have accurate positions for all of this, then the orbital period will be able to be refined much more. Now, a comet can be made to go on a bigger orbit too. If Jupiter's ahead of it, as you can see here, it will go be modified by Jupiter, but sort of pulled ahead a little bit, and the orbit will become longer. So it can work both ways. Now this looks like a really lousy photograph. Fuzzy stars, hardly no sharp detail. This is 1/20th of a 35 millimeter slide. So it's actually a terrific picture. It's just that it would be the size much bigger than the whole wall in the front. It was blown up properly. It's very sharp, but when blown up like this, it's difficult to pick out anything in it at all. But I'm going to. All right, here it is. This little guy right here. See that little fella? This is the second picture taken of Comet Hale-Bopp. And this was taken on May 29th, 1995. The previous picture was taken in 1993 at the Anglo-Australian Observatory. Both of these pictures were taken before the comet was discovered in July of 1995. The Anglo-Australian Observatory photograph was taken with a big Schmidt camera. This one was taken with an 85 millimeter lens during a photographic shoot that I made in Arizona to illustrate my book, Summer Stargazing. And after the discovery of the comet, a call went out from the place where they determine the comet orbits, the Central Bureau for Astronomical Telegrams, where, with such a quaint name, where Brian Marsden, the fellow I mentioned earlier who does comet orbits, works. And I had remembered that I'd taken a picture that might include this. And with the help of Doug George, who's in the audience tonight, who has more expertise in this area than I have, we determined that this was, in fact, Comet Hale-Bopp. It was a pre-discovery photograph, the second and only one of two pictures taken before the comet was discovered. And there it was on my desk. And you can see why I didn't discover the comet. Even if somebody had told me it was on that picture, I still couldn't have found it, unless I knew where the position was. And we could only do that from backtracking from the known picture positions after it was discovered. Anyway, it was quite a thrill to be very, very peripherally involved in this incredibly famous and spectacular comet. All right, let's now go with the video that I mentioned earlier, and I will attempt to narrate this, and Doug George and Peter Sarabolo are in the audience, and you can correct me as we go along. But this is part of a 45-minute video that was made of this adventure of photographing this comet and making the best movie of it. Now what we're seeing here is the nucleus of Comet Hyakutake. This is an animation, of course, as it's flying through the asteroid belt. And it conveniently passes by a couple of asteroids just to give it a photogenic background. The asteroid belt is not quite as crowded as this, but there it goes, this 2 or 3 kilometer. Actually, what this is a good example of, it shows you the difference in size between Comet Hyakutake and Hale-Bopp would be about that big. So this is a flying chunk of ice, a couple of kilometers in diameter, and now heading inward toward the sun. moving through the asteroid belt and coming closer and closer to the sun. And when it gets to around the orbit of Mars, it gets heated enough so that the ice is vaporized. And now we're on the nucleus. This is wonderful animation made right here in Ottawa. This is spectacular stuff. We're right on the surface of the nucleus, and we're looking toward the sun, which will rise here, I think, in a moment. And we're seeing the surface below us actually being vaporized and shooting out into the vaporous cloud around the comet. And it's sunrise on the surface of the comet, and it's really active on the sunward side. And no, I was wrong about the sun. It's now shining down on it, and it's going to, because of the rotation of the nucleus, it's now, we're turned around toward the night side, and now we see all the vapors rushing back, being pushed back in the gas tail by the sun, by the solar wind. Okay, here's the comet again. Here's the orbits of, you can see how close it passed to the Earth there as it flies through the inner solar system. The planets are whipping, obviously this is speeded up, huh? And there it whips past the Earth, and now dives around the sun, and goes down underneath the plane of the solar system. Terrific animation. It really does show what that comet did. And now we're closing in on, again, the comet. There's the little nucleus and the cloud of vapors around it. Presumably heading back out now, away from the sun. Now in the next sequence, back to the frigid deep freeze of the outer solar system. Here's another animation showing the comet passing the Earth. It looks like it's just brushing the Earth, but of course that's just perspective. The comet is closer to us, I guess, to this viewpoint. But it did come within something like 40 times the moon's distance, which is extremely close as celestial objects go. And this is, again, great animation showing the gas tail and now the dust tail separately. Gas tail always very straight, aiming directly away from the sun. So when you look at Comet Hale-Bopp, particularly in binoculars, you're going to see the two tails, and the gas tail will be pointing away directly from the sun. Now here's this wonderful movie made up of 4-minute exposure pictures, and hundreds of them made with precision and great difficulty by Peter Saravolo, using a camera of his own design, taken atop a mountain in Arizona, the same mountain that I took some of those earlier pictures you saw. But isn't that wonderful, the way you can see actually the hourly change in the structure of the gas tail of the comet? It's very difficult to match these slides, and it was done by writing a special computer program that Doug George, the other collaborator on this. The animation, I should mention, I think I'm correct, is John Buchanan do the animation?
Yes.
He did. Okay. All that previous animation you saw was another Ottawa astronomy enthusiast who was responsible for that. So, you know, I didn't have anything to do with this, so I can say how great this is relative to, in particular, to the fact that it's local. But this is the best footage, motion picture, effectively motion picture, putting a bunch of still pictures together, footage of a comet ever made in color. And this was attested to by astronomers at the American Astronomical Society meeting that Peter and Doug took this video to and showed to research astronomers, and they acclaimed it as the best of its type ever made. So these truly are magical objects that change right in front of our eyes, from, in the case of this, hour by hour. In the case of Hale-Bopp being something bigger, probably the changes are day by day. Now, here's Paul Boltwood, another Ottawa area astronomy enthusiast who's a computer whiz, and he's built his own CCD camera, electronic camera, and he's zoomed right in close to the nucleus of Comet Hyakutake to produce this, showing the jets emerging as the comet's nucleus is rotating. And again, this is real research level stuff that is being done by backyard astronomers who have expertise in certain areas. I mean, Peter Sarabolo is an optics expert. Doug George, computers, and John Buchanan for the animation, and Paul Boltwood for the particular specialty that you saw illustrated there. Now, let me just step out of the light here so that I can see better what's going on. Is this Hale-Bopp?
Yes.
Yeah, okay. Okay, now, there's the Earth. There's Hale-Bopp. Womb down going around the other side of the sun from where the Earth is. I think we get some more of pictures of this. Here's the Earth and Hale-Bopp's position in the sky, and you could see where the tail was the longest. That's the point where we are now. All right, so here's the third planet, Earth, I think here. Yes. Okay, that was when Hale-Bopp was closest to the. Okay, we'll have to go. Can we stop this and just go back, please? Back a bit. So back a little bit more there. Great. We're running it frame by frame. This is terrific. Okay, here's the Earth. There's the sun. And at this point, what is this point? Closest to the sun or closest to the Earth? Or neither?
Neither.
It's just a line of sight. Okay. So the comet is moving around, and presumably somewhere around here, it's going to be at its closest. Yes, that looked like something like last February or so, early February. Comet's tail's getting bigger, approaching the sun, approaching the Earth. And now we're moving into March. And we should be getting close to the nearest point to the Earth. I assume that that's it, the nearest point to the Earth. And now you can see the viewing angle slowly gets a little bit worse as the comet retreats and now goes through the plane of the solar system. That will be later in April, much later, at the end of April. The closest point to the Earth was last weekend. The closest point to the sun is this coming weekend. So we're right in the prime period. And you can see how it very rapidly fades once it gets below the plane of the solar system. And the southern hemisphere, that looks like the plane crossing there. And then it rapidly fades just in time for the people in Australia to look at it. But they've had a lot of good comments, so we get our turn this time. Okay, thanks for the video, and we'll go back to the slides. Next, please. All right, so here we are in our night sky. Well, let me put it this way. My night sky, I live deep in the country, and you can always access those, of course, by a little drive if you live in the city. And if you're lucky to live in the country, this is roughly what you'll see. This is where the comet was in the evening sky, facing northwest. Here's the W of Cassiopeia. There's where it was mid to early March. Here's where it was recently. It's in this position now, not far from the Andromeda Galaxy, about 5 degrees. And by the time the sky's clear, it'll be in this area. And you can see in this little, this is, I think this is April the 1st here. No, I think this is April the 1st, and this would be sometime in the next few days. You can see from this little drawing here that the tails are longest here, indicating that that's when it's brightest. This is just a rough guess, but probably isn't going to be too far off, that the comet will be at its brightest sometime between the very last days of March and about the 6th of April. But the whole period from now through to about the 10th of April, the comet is going to be at its best. And that's where it'll be, about hand span being, fingers spread out from the thumb to the little finger, held at arm's length above the horizon. But you've all seen it, and it's not difficult to find. Starting about here, the moon's going to interfere, and by the time the moon is gone again, we're here. So clearly, right now, we're in the best period that we can be in. We're running out of time here, and I'm just going to mention that there has been some, this came with somebody's American Express bill, and you can see that this is a quickie ad here. It says, watch for the Hale-Bopp. Travel to the moon and beyond with our 525 power telescope for, the price isn't on it, but it's something like $175 for this telescope. This is what I call, and has been referred to as a Christmas trash telescope, in that you see these all over the place in camera stores, and they're really, I guess they're better than nothing, but just. And you can tell when somebody's trying to sell a telescope to an impulse buyer. You'll see these outrageous magnification claims, 525 power, 650 or 450 or somewhere in that area. The telescopes clearly are vastly exceeding optical theory in doing that. You can't see anything out them. It just is almost impossible. And they're just playing on, just throwing you big numbers. If you already have one of these telescopes, you have my sympathy. And if you don't have one, I'd really suggest that you visit a specialty telescope store and spend $500 or more, and you'd be much more likely to get something that'll last a lifetime and be worthwhile. And in lieu of not spending $500, do this. Get a binocular attachment, binocular tripod adapter, and put the binoculars on a camera tripod, and you'll get wonderful views. Binoculars actually are the ideal thing to use for Comet Hale-Bopp. Much better than a telescope, at least one of those little telescopes. Certainly not much better than a really nice telescope, but if you don't have a telescope, this is the way to go. You get a lot of astronomy out of binoculars, particularly if they're studied in this fashion. Well, I haven't mentioned too much about comets throughout history, and I'll just briefly do so. But here's, in 1066, King Harold certainly took this as a bad omen. Here's one of his lackeys here telling him that there's a comet outside, sir, and here's what it means, and it was bad news. And comets have been regarded as bad news throughout history. Here's a century-old cartoon from a French magazine showing what the comet of 1857 was going to do to the Earth. And we hear the same thing about Comet Hale-Bopp. In fact, you can find on the internet web pages that are devoted to the apocalypse that's going to occur because Hale-Bopp is going to crash into the Earth when I won't get into the ridiculousness, nor even suggest that you go look it up. But it's there. This stuff never goes away. And yet, The ancients were right. Comets are bad omens when they come close. This was the Tunguska event of 1908, which was a comet or an asteroid that knocked all of these trees down in Siberia, killing some reindeer and knocking the nearest human unconscious who was 60 kilometers away when this thing crashed down into the tundra. This was an asteroid that hit in Arizona, but produced a beautiful crater, and comets do the same thing when they strike the Earth. And we indeed did get a comet that hit not the Earth, but Jupiter, to tell us what is the danger and the consequences of comets smashing into a planet. This comet trailed 20 pieces because the comet was broken up by Jupiter's gravity from a previous close pass of the planet. The comet's chunks, which were maximum of a kilometer in diameter, smashed into Jupiter, producing incredible explosions. This feature is about twice the size of the Earth. These are the blemishes from something just a kilometer in diameter blowing up as they wonked into Jupiter's atmosphere and essentially were vaporized and exploded with the force of millions of hydrogen bombs. So these objects are a danger, and it was very, very refreshing to look and see it happening to another planet as opposed to very, very scary to have something like that happen to our planet. But in fact, it has happened. And if we'll just change the tray here for just a moment. We've got just, I think, 4 or 5 more slides, and then we'll have a question period. Okay, so Jupiter then is actually the recipient of 1,000 times the impacts that ever occur on the Earth. And that's per unit area, not for the whole planet. It'd actually be about 1 million times the number of impacts that the Earth has. Jupiter, in a way, is a protector of the Earth because it sweeps up comets, and the Earth is believed to and is suspected that it would be hit 1,000 times as much as it is if Jupiter wasn't there, acting as the bully and punching out all of these comets as they came into the inner solar system. The blemishes on Jupiter were visible in little backyard telescopes. Just astounding when you think of something a kilometer in diameter, the power that has when it hits something, and the two of them collide at about 150 times the speed of a rifle bullet. It packs a real wallop. Here's a miniature, very miniature example of what happens. This is Michelle Knapp. She was inside doing the dishes or her homework or in the house, and heard kaboom outside, came running out, and this was the back of her Chevy Malibu that she just bought from her grandmother. And of course, her grandmother only drove it to church on Sundays. And she called the police that somebody has vandalized my car. And so the police came and they looked at this, and underneath here was a meteorite about the size of a football. And it had gone right through the car. And so they looked at this rock, and they looked at the car, and their police report, and this is true, the initial police report said damage to private property caused by a very strong male. Or gorilla, perhaps. Because nobody had any idea what the heck happened. The only thing they could think of is that some person, gorilla, walking down the street with a football-sized boulder came and threw it through somebody's car. Well, when this, of course, reached the news media, of course, it was figured out right away what this football-sized rock was. If we could interview the dinosaurs, we'd find out what happened, what it was like when a chunk, likely a comet, about the size of Halley's Comet, hit in the Yucatan Peninsula. And here's the dinosaurs in North America saying, something's up. And here's a kilometer-high tsunami or tidal wave coming toward them from the impact. They say, whoop, what the, as this thing washes over well into the continent, and subsequently the explosion would produce, turn days into nights for years thereafter because of the dust and junk thrown up into the atmosphere from the collision, all kinds of effects from it that utterly changed the climate and wiped out the dinosaurs. This is the leading theory, at any rate. This is the power of the what's called the Cretaceous Tertiary impact that presumably wiped out the dinosaurs. And this is Tunguska, the one from 1908. And this just shows a scale of size here. This is 1 kilometer. This is something like 30 meters. And here we have something like 10 kilometers. And then how often it happens. Once every 200, 300 years or so for a Tunguska. Once every 50 to 100 million years for a dinosaur wipeout. And something like Hale-Bopp hits the Earth. We can have the lights up now. And the slide projector off, please. Something like Hale-Bopp hits the Earth about once every 300 million years to 1 billion years. There was an extinction much worse than the Cretaceous Tertiary extinction that occurred 245 million years ago at the end of the Permian period, which apparently was caused by something as big as Comet Hale-Bopp hitting the Earth. So now I loop around to the final point that these things can destroy life, as the impacts have in the past, but it's quite possible that they started life in the first place by being the source of the water on our planet from which life emerged. So I've gone a little bit over time, but I hope you have enjoyed our Hale-Bopp and Comet tour. Thank you.
I think you'd agree with me that it was more than enjoyable. It was absolutely tremendous, a very pleasant experience, and the imagery, the photographs were unbelievable from my point of view. So thank you very much for joining me again to say thank you to Mr. Dickinson, and we look forward to seeing some of you to view the comet here at the museum. I'll just mention that on tomorrow night there's an evening in French, okay? We have another evening, an English evening, scheduled for the 27th of March. And then, hopefully, next week, when the sky is clear, April 3rd and April 11th. Those are evenings that are already scheduled. So if you want to come and call the number, call and make a reservation, and we'd love to have you. So thank you again, Mr. Dickinson. It was very enjoyable.
We can have a brief question period now, but were the 3rd and the 11th, Margaret, were they telescope viewing nights?
Yes.
Telescope viewing on the 3rd and the 11th from here, weather permitting, of course. So you will probably be able to see that sort of spiral galaxy structure in the nucleus with the telescopes that will be here. It should be quite easy to see. Okay, some questions? Yes. What tilted Uranus off its axis was probably a collision between protoplanets. That is, there was a lot more planetary-sized bodies in the solar system during its formation. And the 8 that remain became the masters of their territory. And anything smaller that was around, but still quite big, was either crashed into these early forming planets, or came close to them and their gravity shot them out of the solar system. And the thinking is that for Uranus, very early in its formation, that we're going back to the first 100 million years of the solar system's existence, that during that time, something maybe a third the size of Uranus, a giant planet perhaps in formation that hammered into Uranus. It would take something like that to do it. Something really big in order to knock a major planet over on its axis. Hale-Bopp, for example, hitting the Earth and producing the end of the Permian era extinctions, where something like 99% of the life forms on Earth became extinct. Vast changes in the nature of life on Earth occurred. Climate being completely changed, devastating changes. Even marine life was almost totally wiped out. Not completely, but a lot of it was gone. Something like that would not waver the Earth from its axis. It takes a lot more than that to knock a planet off its axis. And you'll be hearing stuff about this, about the planetary alignment in the year 2000, on May the 5th or the 3rd, the year 2000, which isn't really an alignment. It's just that of the major planets, the naked eye planets, they'll all be generally on the other side of the sun, and the Earth on this side. A lot is being made of this. The Earth is going to get yanked off its axis by the gravity of those planets, when in fact, the two major planets gravitationally affecting the Earth are Venus and Jupiter. And both of those have very, very much less than 1% of the effect of the Moon. And when they get lined up, it's an insignificant addition to the kind of gravitational tug we already get from the Moon and the Sun. And the other planets don't count at all. They really don't even measure hardly at all on the scale of things. So if Jupiter and Venus line up every 4 years or so, which they do, and that doesn't affect us in any way that can be detected, having the rest of the planets line up is not going to add up to anything. So I just add that answer to the question, because you're going to hear a lot about this. The gravitational pull of the planets on objects on the Earth is less than the gravitational pull that you're feeling from the person that's sitting beside you in the audience. It's very, very small. Yes?
When a comet recedes from the sun, does the dust and the gas coalesce back into it, or does it lost its place there?
In the case of Halley's Comet, it loses about 1/10 of 1% every pass close to the sun. And it comes about the distance a little bit closer than Venus. In the case of Hale-Bopp, it loses 1/1000th of 1% of its mass on each trip. So it'll be good for many, many, many more trips. And it depends on how close the comet gets as to how much is vaporized. And then when it gets far enough away from the sun, like out past the orbit of Mars, essentially that vaporization quits. Anything that has been turned into vapor and released from the gravity of the nucleus, which is easy to do because it's so small, is lost. So they do lose mass every time they come in. They don't gain it when they go out, because they're just going through essentially a vacuum. And when they come in again, they get a little bit more vaporized off. There are comets that only last for one trip. They come within, either crash into the sun or come within one solar diameter of the sun, and those comets very rarely survive. The heat is so tremendous they get vaporized within hours. Yes? looked like a piece of hot metal. Yeah. Yeah. Yes. Okay. There were two questions. One is in looking at the comet, does the tail appear to shimmer or pulsate? And it does, but that's an optical effect. There is an effect to the eye that, particularly if you're staring at something and really concentrated on it, that will have that kind of effect. And it's just it's the muscles in the eye, because you when you look at something and you think you're looking at it steadily, actually the muscles in the eye are constantly keeping it in that position. So there's this kind of effect is going on. Yeah, that effect is in your eye and the eye-brain connection. And what you might try, which is another effect, but it's also in the eye, is to look away from the comet but concentrate on it. This is called averted vision, and you'll see the tail more clearly, because the peripheral vision of the human eye is more sensitive than the straight-on vision to faint light. And this is an evolutionary selection effect. This is because there was a time when we needed at night to see the saber-toothed cat jumping at us from the side. And the people who survived and saw the cat we have their genes. And the people who didn't have the good peripheral vision, the cat got them. So that has survived to today, and you can use it in astronomy in that way. Now, your other question was about this piece of like molten metal flying straight down. That was a daylight fireball. That would have been at night. That would have been a meteor so bright that it would have lit up the whole landscape like full moonlight or brighter. And what it would have been something about the size of a baseball, or perhaps a football, coming into the Earth's atmosphere, like the one that hit Michelle Knapp's car. Probably not that big. Probably more like a baseball or a fist-size object. It depends on how close you were to it. Every time there is one of those, I get a lot of calls from people, and then I pass those calls along. There is a national network of astronomers who collect the calls and then disseminate them to the other members of this network, which includes meteor specialists, including some here at the Geological Survey and at the National Meteorite Collection. It has an acronym which I've forgotten. But at any rate, I cooperate with this group by funneling reports to them. And if you get enough, you can tell where the thing came down, and if it was big enough, go and look for it. And this happened in Quebec 2 years ago, and they found pieces of it. Quite a nice pile of chunks. Yeah. You know, did you hear anything? Yeah. Yeah. What it usually means is that if you don't hear anything, that it burned up before it got into the deeper layers of the atmosphere and was able to produce an audible. The atmosphere was dense enough to propagate the sound. But a daylight fireball is wonderful. I've only seen one. Yes, I did. I got lots of reports of that one. Everybody was out enjoying the nice day, and especially in Kingston. But I also got reports from Toronto where they looked the other way. See, you were looking west, right? And people in Toronto were looking east. And we did get enough reports on that, and it fell just north of Colborne, Ontario, near Port Hope. Nothing was ever found. If it fell, what I'm saying is, if it fell, if it reached the Earth. So, I bet you're really astonished that it was like 100 kilometers away from you. Yeah. 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 Most people think they're a lot closer than they really are, but they're typically 100 kilometers away and about 30, 40 kilometers up. Okay, well, that was an interesting one. Yes?
What factors distinguish the orbit of the comet? Like, what distinguish how does it come back? How does it know when to come back?
How does the comet know when to come back, and how does it travel in that orbit? Well, once it's in an orbit, unless something affects it, it follows the same orbit again and again and again. It's absolutely gravity, yes. Just in the same way that the Earth orbits the Sun, and the Sun is the controlling gravitational influence, and the Earth orbits that. The Moon orbits the Earth, because the Earth is the more massive body, and it's the gravitational controlling influence. On the case of a comet, it also orbits the Sun. And once it's in an orbit, the only thing that gets it out of that orbit is gravitational influence from the planets, just like Hale-Bopp was affected by its pass something like 50 million kilometers from Jupiter. And Jupiter's the main influence because it's next biggest after the Sun. But the Sun defines the focus of the orbit. And those comets that are floating around in the Oort cloud, beyond all the planets, they're the same thing. They're orbiting the Sun too. They take them 1 million years for one orbit. So the Sun has controlling influence out to about 2 light years from.
So we can use this color really far and then keep it.
Yeah, when it's really far out, it's just a frozen chunk, and then when it gets close, it gets vapors. Was there a question here? Yes. How do they figure out the orbits of comets and how long it takes for one revolution? The way they do that is they observe it very carefully. They look at the comet against the background of the stars, and we know where the stars are. They're all fixed in position. So you watch where the comet is as it moves, and you can figure out how far it has moved in a certain time, and if you follow it long enough, you can determine exactly where it's going using the Earth's motion, your position on the Earth, observations made at different times. You can triangulate. You can tell exactly how far away it is and what path it has. So then you extrapolate, which means that you extend what you know to what you don't know, and you can make the whole orbit. It's not easy. It's mathematically rather complex, but it's understood very well because Isaac Newton figured it out. And then Edmund Halley looked over his shoulder and said, "Whoo, that's neat stuff." And he took Isaac Newton's equations and he applied them to comets that had been seen throughout history, and he said, this is the same comet coming back every 75 years. And that's how he discovered Halley's Comet. He figured out the orbit using Newton's calculations, who's probably the greatest scientific genius of all time. So we've known right back to Newton how to do it, and we've just become more accurate at doing it. So that's sort of the way it's done. Yes?
So can we calculate now when Hale-Bopp comes back in over 2,000 years, what position Jupiter will have to determine
No.
if the orbit will get bigger or smaller?
No, we can't do that because right now the the accuracy in calculating its return date is plus or minus a couple of centuries. But after looking at it for another 2 years or so, they should get that down only, I think, to a decade or two. I don't think it can be done any more accurately than that. The comet has to be watched for a long time. That other end of the orbit is a heck of a long way out there. And a very, very tiny error, a plus or minus, a teensy thing, is going to mean a decade or two of the calculation coming back. So they'll be close, but that's, for a big orbit like that, that's all you can be. Yes?
Have computers revolutionized the science of...
Yes, computers have revolutionized the science of astronomy just as they have all the other sciences. Back there's a very famous and wonderful astronomer, just amazing person, Helen Sawyer Hogg, who passed away about a decade ago. And she went to school, partly at Harvard and at another New England college. And she was in a group of astronomers who were doing calculations for Harlow Shapley, who was the Carl Sagan of his age, in terms of being a popularizer, and was a pretty important astronomer of his age. And what he did, he had all the calculations that he wanted made. And what he would do is he'd take the calculations and he'd go in a room beside his office. And in there were 18 women astronomers who were called calculators. And they were all sitting there with pen and paper doing what a computer does today. And there's a picture of Harlow Shapley and the 18 women lined up in front of Harvard Observatory. I think it says a lot of things, this picture. But one thing that it says is that is how they did it then. And even then, they couldn't do all the calculations that they wanted to do. They were too difficult. It took too much time. And many astronomers spent a lot of time just sitting, doing very complicated equations, math, and just drudge calculations. And every time there's a bigger and faster computer, there's more that the astronomers can do. A lot of this positional stuff, they can also make a galaxy, or they can make the whole universe by inserting the masses of certain things in certain positions, and then letting gravity do its work, and letting the computer run. What will gravity do under a particular situation if two galaxies collide? What will happen to them? And the computer can show us. It's calculations that could never be made before. Computers run telescopes. I have little computers attached to my telescope. Some of those pictures were taken with the telescope guided by a dinky little computer this big, made specifically to do that. The list is endless. It has just revolutionized the science. Telescope optics are designed on a computer, and it would be almost impossible to do the optical designs without a computer to be able to do the number crunching for you. It just goes on and on. Yeah. Yes?
If comets were indeed our source of water, that infers millions and millions of comets. Are we talking about, at some stage, they were more dense than possibly, or are we just talking about eons of time?
Mostly that there was a lot more of them. Back at the origin of the solar system and the origin of the planets, there was a lot of other material in the solar system, including comets. And the number of comets that would have hit the Earth, say 3.5 billion years ago to 4 billion years ago, which is what's called the bombardment period, before life began, there would have been anywhere from 1,000 times to 100,000 times as many comets hitting the Earth as there is now, because there was a lot more then, and they've all hit the planets now